Afternoon or evening, everybody. Welcome to the NASA Space Geodesy Data for Precise Orbit Determination of Altimeter Satellites Earthdata webinar. This is your host, Jennifer Brennan. While everybody is logging in, we have two optional polls at the bottom of the page, and we do appreciate your feedback on these polls. They help us to continually improve upon this webinar series. I've got 2 p.m. Eastern Daylight Savings Time, so we are going to go ahead and get started here. First, what I'd like to do is touch upon a few housekeeping items related to this webinar. To ensure the best audio experience, the conference has been placed in silent mode. However, if you have any questions or you have any issues, what I'd like for you to do is to please enter those into the Q&A pod, and you'll see that located on the lower right-hand side of your screen. This works like a chat. This webinar is being recorded and will be posted to our online Adobe Connect webinar catalog, as well as to our NASA Earthdata YouTube channel within a couple of days of completion. And I do plan to provide that URL to all of you at the end. All presentation files will also be available for download at the end of the webinar. The webinar is 1 hour long. We've allocated 45 minutes to the presentation with an additional 15 minutes for the question and answer period. So after our speaker has finished his presentation, what we'll do then is we'll move to a final set of polling questions. And then from there, we'll transition directly to the Q&A period. Remember, you will have an opportunity to ask your questions throughout all portions of the webinar. And again, what you'll do is you will use that Q&A pod, which will always be on the right-hand side of your screen. Questions will not be answered using the raising hand function. It has been disabled. And then just one final note, depending upon the volume of questions that we receive, we will extend the Q&A period an additional 15 minutes to 3:15 p.m. Eastern Time for those of you who wish to stay on the line. So what I'd like to do next is move to our agenda. Let me pull this up here for everybody. During today's webinar, our speaker will start off by providing an introduction to precise orbit determination and explain why this is important for satellite altimeter observations. Next, he will transition to a more in-depth look at POD with respect to observations, force modeling, reference frame, and polar motion, or Earth rotation. Finally, we will complete today's webinar by discussing applications of precise orbit determination for satellite altimetry. With that, it is my pleasure to introduce today's speaker, Dr. Frank Lemoyne, who is a scientist working in the Planetary Geodynamics Laboratory at NASA Goddard Space Flight Center. Right?
Thank you, Jennifer. The topic I'm going to talk about today, precise orbit determination, is part of the discipline of geodesy, which is one of the oldest of the earth sciences. Geodesy as a discipline today is defined as the discipline that measures the shape, the gravity field, and the rotation of the Earth and how it changes with time. Space geodesy means we use satellite data and satellite techniques to do these measurements. And precise orbit determination comes into play because in order to use or process these measurements or to interpret them geophysically in a meaningful way, you have to know where the satellite is when those measurements are being made. So let me give you a slightly more technical definition. So the problem of orbit determination rests on two pillars. It's the best estimate of a satellite ephemeris that's determined using observations that are influenced by random and systematic errors using mathematical models of spacecraft motion that are imperfect. And so I'm going to come back to these themes over and over again. How well you do depends on the accuracy of your observations. How well you determine where the spacecraft is depends on the fidelity of your mathematical models that describe spacecraft motion. So I'm going to give you a flavor in this talk of how we go about some of the mathematical modeling that we do and what is the state of the art in terms of the observations that we use today. So what do we mean by precise orbit determination? In the past 25 years, it has come to mean determining where the satellites are in a radial sense with respect to the center of the Earth to a few centimeters. on JSON, the altimeter satellites that are in orbit now, the requirement is that we have to know where they are to within 1 centimeter RMS over time. So why do we need to do this? As I mentioned, it's because the analysis of our science observations require a reference that is accurate to this level. It can be the determination of mean sea level. It can be natural hazards, crustal deformation. I see there's a volcanologist logged on. If you want to know deformation on the Yellowstone hotspot and you're using GPS data, the beginning of your analysis requires you to know where the GPS satellites are. And so you import the precise orbits that are determined by international analysis centers to do your analysis. If you want to know more technical information, I would refer you to this textbook that was written by Byron Tapley, Bob Schutz, and George Bourne. The important thing to understand is that we start off with some nominal estimate of the trajectory. We use observations to come up with a best estimate of what the trajectory is, and there's some deviation between our estimate and the truth, and that's a representation of our error. In POD, we always want to minimize those differences. So let me go over a few examples of why it's important. And so the first example comes from the GEOS 3 spacecraft, which was one of NASA's first operational altimeter missions. It was launched in 1975 and operated for approximately 4 years. And it carried a first-generation radar altimeter to map the oceans. And on the right-hand side, you're seeing a plot from a paper by Bruce Douglas that was published in the Journal of Geophysical Research. It shows two collinear profiles in the Atlantic Ocean, acquired approximately 5 months apart. And there's a scale bar there that shows you the scale is about 100 centimeters or so. So you see on the left-hand side of the plot, the two collinear profiles are measuring pretty much the same thing. And so what they're measuring is the height of the ocean surface, and the height of the ocean surface is perturbed by the topography of the underlying seafloor. And there's a seamount there. It produces mass, and so it causes the change in height of the ocean surface. On the right-hand side, there was a big change in the ocean height between April and September on the order of 100 centimeters, and that's because of the change in the location of the Gulf Stream. So the altimeter measures ocean height, which provides you information on the geoid, which is the gravity field of the Earth, and on the changes in the ocean circulation. The second example comes from the measurement of regional and global mean sea level. And NASA and other international space agencies like the CNES and NOAA and EUMETSAT have placed in orbit a series of satellites over the last 25 years to synoptically measure the ocean height variations. These are TOPEX, JSON-1, JSON-2, and the JSON-3 satellite that was launched just this past January. The crosshatch pattern that you see in the figure is the ground track repeat pattern of that satellite. And so the ground tracks repeat pretty closely to within a few hundred meters every 9.9 days. And so you can stack the observations over time and see how much the height of the ocean surface has changed. And this produces this map of mean sea level change. And you see that mean sea level change is uneven depending on where you are in the oceans. And that's because mean sea level has different causes. It can be caused by thermal expansion and heating is uneven in the different parts of the ocean. Or it can be caused by the addition of ocean mass, and it's influenced by the state of the ocean circulation. So, for example, whether you have an El Nino or not. So this is one of the big motivations for why we need accurate orbits for altimeter satellites, and we need to maintain a consistent level of accuracy over the entire 25 years that we have measurements. Incidentally, if you're interested in this data, I would refer you to this URL at PODAC where you can download these altimeter data sets. The third example comes from studying hurricane intensification, and you might wonder, why is that important? Well, remember that because of thermal expansion, the dilation of a water column, if you have a warm core eddy, it's going to have a height, the height of the ocean surface with respect to the reference is going to be higher, and you're going to easily measure that with an altimeter. But if you're measuring sea surface temperature, you're only sensitive to maybe the top few millimeters, maybe the top few centimeters of the ocean surface. It's only giving you information on that skin depth. And so you won't necessarily see what is the heat content of that ocean column. But with altimetry, you can infer that information much more directly. So Bob Laban at the University of Colorado has spent a lot of time studying the ocean circulation in the Gulf of Mexico. And shortly after the passage of Katrina over New Orleans, he produced this plot, which looks sideways on my screen. I apologize. But the intent, so what happened is Hurricane Katrina flew up first over the southeast portion of the Gulf of Mexico, and that's the loop current, which is an extension of the Gulf Stream before it goes through the states of Florida. And sometimes the loop current will break off into an eddy, and that's what you see in the center of the Gulf of Mexico. And so Hurricane Katrina essentially flew up the loop current, and then it flew over the loop eddy, and essentially it aspirated energy, and that's how it became so powerful. So you can see that to understand the dynamics of cyclones, you want satellite altimeter data. You want your orbits to be as accurate as possible. And in addition, you want a system that can deliver this altimeter data to you in near real time with orbits that are as accurate as possible, so you can interpret that information properly and feed that information into forecast models. And in fact, on the JASON-2 and JASON-3 missions and other altimeter missions that are active right now, one of their functions is to distribute altimeter data in near real time. If you want more information on this, I refer you to these URLs here in this figure. So on this chart, I'm showing you the suite of altimeter satellites that we have on orbit right now. There's JASON-2 and JASON-3, which I've already mentioned. ESA has 2 satellites on orbit, CryoSat-2, which is primarily a cryosphere mission, but it obtains a lot of useful data over the oceans. There's the Sentinel-3A, which is in its commissioning phase right now, but it will shortly be declared operational. And then there's a mission from ISRO and CNES, which uses a Ka-band altimeter, and then the HY-2A satellite from the Chinese National Space Agency. So for all of these, if you want to use data from these missions or merge data from these missions, you have to determine their orbits as accurately as possible. So what I want to show you here is the ground track pattern for TOPEX and JASON-1 and JASON-2. The ground track pattern is determined by the parameters of the orbit, so its altitude and its inclination. And so the scientist that designed this mission for a variety of reasons chose this particular sampling geometry. As you're aware from different fields of remote sensing, there's always a trade between temporal and spatial resolution. And in this case, they settled on this particular sampling interval of about 9.9 days. And then in this example, a cross-track separation at the equator of 315 kilometers. The higher altitude, 1336 kilometers, was chosen because they wanted to minimize the orbit perturbations due to atmospheric drag, which might cause problems in determining where the satellite is. And this is an example of another ground track pattern. So on the left, you have the ground track pattern from the TOPEX and JASON satellites. And on the right, you have it from the ERS or ENVISAT satellites. And they made a slightly different choice for their synoptic mapping. They wanted a ground track repeat over 35 days, which gives them denser spatial resolution at the cost of slightly less temporal resolution. Just another comment, the altitude at which the satellites fly is extremely important. When you're down at 800 kilometers, you are much more sensitive to atmospheric drag, and operationally, it means you also have to have more maneuvers to actually maintain your orbit. So this is a schematic of what this talk is all about. If there's one slide that summarizes this presentation, this is it. So you have a spacecraft that's flying in orbit. It has an altimeter that's measuring the range to the ocean surface as a function of time. It's tracked. Typically, there's a retroreflector on the satellite that returns precise reflections from lasers that are sent from satellite laser ranging stations on the surface of the Earth. On the JASON 1, JASON 2, JASON 3, and the other altimeter satellites, they also carry a Dorris receiver. Dorris is an acronym for a Doppler tracking system that was developed by the French Space Agency and the Institut Géographique National in France. And it consists, as I'll show later, of Doppler beacons that send out radial signals that are received on board the satellite. And then finally, the third tracking system is if you have a GPS receiver on the satellite, then that tells you where the satellite is. The information that you get, once you know where the satellite is, you can determine the sea surface height, which has two components. The sea surface height is the height of the ocean surface with respect to a reference ellipsoid. It tells you what the geoid is, which is the gravity field over the oceans, or the dynamic topography, which is the change in the ocean surface due to all the oceanographic processes. So the geoid is typically on the order of plus or minus 100 meters over the globe, and the dynamic ocean topography, you're talking on the order of 2 meters. So that's the size of your oceanographic signal. So this is another schematic of what orbit determination is all about. So you always start with your onboard tracking systems. You need geophysical models that tell you mathematically how the orbit evolves under the influence of the gravity field, under the influence of the solid Earth tides, the ocean tides, and how time variable gravity changes on the surface of the Earth. You need mathematical models that tell you how atmospheric drag influences the satellite orbit, and as I'll explain, how other surface forces like radiation pressure change the orbit. These are quite complicated. You need a reference frame, and that's essentially telling you where your tracking stations are as a function of time, and that reference frame has to be stable over the entire time period over which you're interested in doing the analysis. You need to know how the Earth wobbles as a function of time, that's polar motion, and you need Earth orientation parameters. Specifically, you need to know how the Earth's rotation changes on a day-to-day basis. So first, I'm going to give you a brief summary of the different tracking systems that we use today. So the tracking system that's been around essentially since the dawn of the altimeter era has been satellite laser ranging. The first satellite laser ranging was done in 1964 at NASA Goddard, actually at the Greenbelt site, just a few kilometers from where I'm sitting. There's a network of stations around the world that routinely send laser pulses up to satellites in orbit that have retroreflectors, so they track science satellites, and it's all operated under the umbrella of an international service called the International Laser Ranging Service. You'll see that one of the issues is there's a preponderance of stations in the northern hemisphere. The best stations of the network have precision on the order of a few millimeters, up to 5 millimeters or so. And you see examples of two of these stations, one at Haleakala on Maui. It actually is close to the summit of Haleakala, and at Yarragadee in Western Australia, which is one of the most productive sites in terms of quantity of data of the SLR network. So this slide gives you an idea of how SLR precision has evolved with time. Remember on the introductory slide, I said how well you can do an orbit determination depends on the quality of your observations. So you can see around the time of GEOS 3, we had single-shot precision on the order of a few decimeters. The same for CSAT as well. There was a big change when new technology was introduced in the early 1980s, and then you had precision, single-shot precision on the order of a few centimeters. And by the early 1990s, ostensibly in preparation for the launch of TOPEX, we had systems that had a precision on the order of a centimeter or so, and there's been improvement and evolution in some of the stations in the network so that some of them even have precision better than that today. If you want more information, I refer you to John Degnan's presentation below. So what does that do for TOPEX and JSON 1 and JSON 2? An SLR tracking pass for these satellites over a ground station will last 15 to 20 minutes, typically horizon to horizon. And because of geometry, you might get 2, maybe 3 if you're lucky, tracking passes per day. So in total, these satellites will get between 20 and 30 passes per day from the different stations of the global network. In the lower right-hand side, I'm showing you a detail, sort of a histogram of the number of passes that were collected by the different stations of the global network between February and March of 2016. And we're looking specifically at JSON 2 and JSON 3 because we wanted to compare the tracking for those satellites. JSON 3, having been launched, was placed in an orbit that was 60 seconds apart from JSON 2. So the two satellites were essentially flying in formation. And that's to calibrate the altimeter and the radiometer and to make sure that you can actually connect the data, altimeter data from the two time series. And so the two peaks in this histogram, they're the stations that have tracked these spacecraft the most, and they are Yarragadee and station in China called Changchun. So the second system that we use to determine where an altimeter satellite is the French Dorris Doppler system. It consists of about 55 to 60 stations around the world. As I'll show you momentarily, it's the network that has the most homogeneous distribution, and that's by design. There are beacons that transmit on two frequencies, 401 megahertz and 2 gigahertz. And then you have a receiver on board the satellite that essentially measures the Doppler signal. In the early days, in the 1990s, the Dorris receivers had only one channel, so they could only track one station at a time. And then later, satellites that were launched, the receivers could track up to 2 channels at one time, so 2 Dorris stations if they had 2 Dorris stations in view. And all the current satellites, JSON 2 and so on, they use what is called a DGXX receiver, and it can track up to 7 Dorris beacons if you happen to have that many in view. And the advantage is, as I'll explain when we get to GNSS, it gives you much more data in order to be able to pin down what the spacecraft is doing and how well you can do the orbit. So this is a representation of the Dorris network as of this month. And if you want more information, I would refer you to the website of the International Dorris Service. So how has the Dorris network evolved with time? Going back to the theme that I mentioned at the beginning of the talk, you can only determine your orbits as well as the quality of your observations. So that's represented in these two charts where, as part of the work we did for ITER 2014, we looked at how well we could determine the station position over 7 days, first in 2000, using the network and the data that existed then, and then in 2014, using the network and data that was available at that time. And the size of the circles gives you an idea of essentially the positioning precision. So it tells you something about the quality of the data. And you can see that over the last 14 years, the positioning precision has improved tremendously. And this is due to design changes. There have been improvements in the monumentation stability. We have more satellites, so better geometry. And because of the changes in the Dorris receiver, in other words, it has more channels. So if you would like more information, I would refer you to the paper by Guillaume Moreau, which is in press. And if you want to learn about the monument changes, how the monuments were made more stable, and how the radioelectric environment was made more favorable for the propagation of Dorris signals, I suggest that you look at the paper by Hervé Fagard. So I'd be remiss if I didn't talk about GPS. It's one of the prime tracking systems on the JASON series of satellites. On TOPEX, there was a TOPEX demonstration receiver. And the GPS system consists of two elements. The first, obviously, you have the satellite constellation. And the second is you have the ground receivers. And then the third, you have your satellite receiver. Typically, before you determine where your satellite is, you have to do a determination of where your GPS satellite constellation is. And what most people will do is they will go to the website of the IGS service and download a solution produced by one of the international analysis centers. And that's the first step in determining where your altimeter satellite receiver is. So the IGS network today has hundreds and hundreds of sites around the world, and they all stream data to the IGS data centers, including the NASA CDDIS. So what does it do for JASON 1 and JASON 2, and in fact JASON 3? Both those satellites are equipped with receivers that were developed at JPL, and on average, they track 8 satellites at one time. And so that means that every epoch, so typically every 10 to 30 seconds, you have a tremendous number of observations. And the observations, you can think of them as ranges from the satellite, from the JASON satellite to where the GPS is, over a wide array of geometries. And so that gives you tremendous geometrical strength, and it's why GPS is so useful. So how do we use this data? The data density from GPS and also lately from Dorris, because you have so many observations, it means you can adjust very many empirical parameters. You can compensate for deficiencies in your orbit model. And if you intercompare this reduced dynamic approach with orbits that don't use as many empirical parameters, then you can improve your underlying dynamical models. And all this approach was laid out in this paper by Xian Wu in 1991. So why do we need multiple tracking systems on a satellite? First of all, it's to establish orbit accuracy. And that's especially important for an application like mean sea level change. And the second is for redundancy in the event one of the tracking systems failed. And that does happen on occasion. For example, on the GeoSat follow-on spacecraft, which is labeled GFO on this slide, the GPS system didn't work. It failed very early in the mission. And so the U.S. Navy would not accept the mission until we at NASA actually demonstrated that we could deliver sufficiently precise orbits using satellite laser ranging data and altimeter crossovers. And the second example is on the Jason 1 spacecraft, where the Dorris oscillator essentially misbehaved, and this started happening not long after launch. It was perturbed by passage through the South Atlantic anomaly. And so it took us time to develop a procedure to deal with that problem. But we had the other tracking systems available to compensate. So this is an example of how SLR data are used to validate the quality of independently produced GPS and Dorris orbits. So every point represents a 10-day cycle of an orbit, either computed using GPS in magenta or green, or blue with Dorris. And the SLR data are independent, and so they give you a completely independent measure of the orbit accuracy. So in this example, you can see that the GPS orbits have a radial orbit accuracy on the order of a centimeter, and the Dorris orbits on the order of about 1.6 to 1.7 centimeters. This is the reason, because we can do these types of intercomparisons and many others like these, that we have such high confidence in the determination of mean sea level change from satellite altimetry. This is another example from the Soral spacecraft, and it's a histogram of the Soral satellite laser ranging residuals to Dorris-only orbits. So again, the SLR data are independent as a function of elevation above the tracking station. And when you're measuring when you're taking SLR measurements at very high elevation, 70 to 90 degrees, you're getting a direct estimate of the radial orbit error. So from this, Nikita Zelinsky in his paper concluded that the radial orbit accuracy for the Dorris-only orbits on Soral was on the order of 13 to 15 millimeters. So now I'm going to talk to you a bit about the geophysical models. So we represent the gravity field of the Earth in spherical harmonics, and essentially a lot of the work in space geodesy over the last, I would say, 40 years has been to how can we improve our estimates of these coefficients, CLM and SLM, and how can we increase the truncation of the expansion that we use. To give you an example of how it's important, we can look here on this slide on the left for essentially it's a spectral decomposition of the gravity field perturbations, the radial gravity field perturbations on the orbit of TOPEX using a sample gravity field. And the perturbations can be up to 100 or several hundred meters at a variety of frequencies. And so if your gravity field model is imperfect, then you will get orbit error at these particular frequencies, and then that will map into your altimeter products. So that's something you want to avoid. Sometime after the launch of the TOPEX mission, we did a retrospective analysis to see how well the then current, and then the previous gravity models did on the TOPEX orbit. And so you can see if we used a gravity model, GEML2, that was developed in 1982, we would only have been able to fit the satellite laser ranging data to that orbit to 100 centimeters. And so it shows you the that all the work that was done in the 1980s to improve the gravity models and the early 1990s really paid off. So the latest gravity models that are derived from GRACE and GOCHE data essentially eliminate static gravity error on the TOPEX and JSON orbits, but we still have to consider in detail the time variations in the gravity field. So we use the data from GRACE. The GRACE satellite were launched in 2002, and they measure very precisely the range between the two satellites as a function of time, to the level of a micron, and you can, from that, infer how the gravity field on the surface of the Earth is changing, and it essentially can be interpreted as the mass motion on the surface of the Earth. And so to give you an example of the detail that we can now see, we can, in the upper part of the chart, you can see the mass change seen by GRACE over the Amazon due to changes in surface hydrology. So where it's red, it's essentially the flood season or the monsoon season in that part of the world. And where it's blue, there's a water deficit, and therefore there's a mass deficit. And on the bottom, you can see a depiction of the mass loss over Greenland, and also obtained from GRACE. So one of our challenges in satellite altimetry is how best we can actually use this very detailed information from GRACE, which is not always available. The data has gaps due to aging of the spacecraft, and it's not available with a latency that we can actually use for the operational delivery of altimeter much sooner. So we have to use other strategies. But we very much use the data from GRACE. So now I'm going to talk to you about the surface forces. I already mentioned that we have to consider atmospheric drag. Another one of the surface forces is radiation pressure. So the best way to explain it is by comparison. So I'm showing you here the magnitude of the perturbing forces on the GeoSat follow-on spacecraft. And there's a picture of it in the right-hand side of the figure. And so you can interpret this as typical for a satellite that's at that altitude of roughly 800 kilometers. And so you can see that for C2020, that's a perturbation on the order of 10 to the minus 7 meters per second squared. Ocean tides are on the order of 10 to the minus 6. Moon and sun third body are 10 to the minus 6 to 10 to the minus 7 meters per second squared. So that means your orbit model has to include a solar system ephemeris. And solar radiation pressure and atmospheric drag are typically 10 to the minus 8 meters per second squared. And atmospheric drag is highly variable because it depends on the orientation of the spacecraft, the atmospheric density, and where you are in the solar cycle. So for example, in the histogram on the right, you see the magnitude of the solar radiation pressure in blue, atmospheric drag in red, and then the perturbation due to planetary radiation pressure. So photons exert pressure even if they're reflected from the Earth or even if they're emitted in the infrared. And so on the GeoSat follow-on spacecraft, the radiation pressure perturbation, solar radiation pressure, is roughly constant at about 50 nanometers per second squared. But drag changes depending whether you're in an intense solar activity period or not. And on this particular example, it changes by a factor of 10. So that's why the altitude at which you have an altimeter satellite really matters. So I mentioned that photons exert momentum on a spacecraft, and how they exert momentum and how they change the trajectory in a spacecraft depends on its properties, whether you're talking about diffuse reflection, specular reflection, whether the photon is absorbed. it can get enormously complicated because if you want to do things right, then you actually have to follow a ray tracing algorithm. But do you really need that complexity, and can you afford that computationally? So in the beginning, most people just used a cannonball to represent the spacecraft. But very early in the planning for the TOPEX mission, that was realized that was not sufficient. And so Peter Andresian and George Rossborough at the University of Colorado did a finite element analysis to analyze what the accelerations were. From that, Andy Marshall and Scott Lusky at the Goddard Space Flight Center developed sort of a computationally simple model, which you call a Boxwing, and it would developed parameters that were fits to parameters on the micromodel. So the advantage of the Boxwing model is you could implement that very easily in your orbit determination software. You don't need to run a finite element model at every integration time step. And for a long time, these macro models, these Boxwing models, were the standard, and actually still are the standard, are for computing radiation pressure forces. They have some disadvantages because they don't account for self-shadowing, and most of the time they don't account for thermal emission as the spacecraft enters and exits shadow. So one example of an improvement that you can do is done by Marek Zibard at University College London, and that's to develop a detailed mathematical model of the spacecraft, and then essentially illuminate it from different sources, use ray tracing to calculate the radiation pressure accelerations as a function of orientation. And you package that compactly, and then you can access that information when you're computing your orbit. But you have to decide whether that extra effort is worth it. And for altimeter orbit determination, we say that it is, because it removes systematic signals that would otherwise contaminate your altimeter data. So now I'm going to show you a video that represents the orbital motion of the JASON-2 spacecraft. And so you see here this video. It represents the orbital motion of JASON-2 orbiting the Earth. And as you can see, the orientation of the solar arrays with respect to the sun and how they change with time are going to affect how you compute the radiation pressure accelerations. And in fact, if you're going to use a Boxwing model, then you have to know how the spacecraft is oriented essentially continuously. Otherwise, you're not going to make any meaningful computations. But as you can see in this particular example, where the spacecraft was doing a change in yaw steering attitude, that can get quite complicated. And so for TOPEX, we had a complicated array of tables and accompanied by a complicated algorithm or subroutine that essentially told us how the attitude changed as a function of time. And it was probably accurate to within a few degrees. What we learned on JASON is that's not good enough. What we actually need are quaternions, or essentially rotation matrices, continuously, that tell us how the spacecraft is oriented and how the solar arrays are oriented. And if you misorient the solar arrays, which are essentially, you can think of them as solar sails, even by a few degrees, that will introduce systematic errors in your altimeter data. So we can go back now to the presentation. So if you want to see more of these videos, I would refer you to this URL. So now I'd like to talk to you briefly about the reference frame. So the reference frame underpins everything that we do in altimeter satellite POD because it tells you where your tracking stations are. And it's based on data from satellite laser ranging, GPS, Dorris, and another technique called very long baseline interferometry. It's combined mathematically to produce what they call is a realization of the reference frame, which is shown here. It's a set of positions and velocities of these reference points. On the top is the horizontal velocity field for the latest solution, ITRF 2014, and on the bottom are the vertical velocities. And the vertical velocities, you can see, for example, over Hudson Bay, the vertical velocities are very high. That's because of post-glacial rebound. The same is true over Scandinavia. You can see the vertical velocities are high off the coast of Alaska, for example, near the Yakutat region, or on the coast of Greenland. That's because of the glacier withdrawal and the ice melt in those regions. But then you can see some probable outliers in different parts. So, for example, near Bangladesh, or a particular station that looks like it's in Colombia. So when you get a new solution, realization, you have to evaluate it pretty closely before you begin to use it. What happens if you misrepresent your reference frame? That was looked at by Brian Beckley in this particular paper, where he looked at the sea surface height trend from differencing orbits that were computed with a reference frame ITRF 2005 with a previous reference frame CSR 95. And in that particular example, it produced errors in the mean sea level rate of about minus 0.2 millimeters per year. But look how at the high latitudes, those errors get amplified. You have errors as high as, it looks like 1 to 2 millimeters per year. So the reference frame has a big impact on how accurately you can determine a regional mean sea level. Now, another parameter that we need to know essentially the polar motion of the Earth. The Earth rotates in an irregular fashion because of different mass shifts. And the true pole can deviate by up to 10 meters from what they call the reference pole. So on a regular basis, we have to be supplied with updates, which are provided by the International Earth Rotation and Reference System Service. That's one of our inputs to orbit determination. Another input that we need is actually the rotation angle of the Earth, which in technical terms is known as UT1. And the Earth doesn't rotate regularly. We know it's slowing down as a function of time due to tidal dissipation, but because of exchange of angular momentum among the different components of the fluids that make up the Earth, either the atmosphere or the oceans and so on, there's a variability in the Earth's rotation, which is represented in the figure on the right. It's called length of day. And those variations have an annual signal. There's an El Nino signal in there as well. And if you misrepresent that, for example, 1 millisecond is 7.4 centimeters on the Earth's equator. So that means that's how far off you will be in all your orbital calculations. So if you don't know the rotation angle of the Earth, you can kiss your precise orbits goodbye. And what I don't think people understand is that the only technique that today can reliably give us the rotation phase of the Earth is a technique known as very long baseline interferometry. And so it's a technique that uses arrays of radio telescopes to record signals from distant quasars. The signals are correlated to give us information about the change tau in the arrival time, which gives you the baseline between the stations, and ultimately it gives you the absolute orientation of the Earth. If we didn't have these routine measurements made by VLBI of quasars, we wouldn't have precise orbit determination. And so today, the measurements are probably less than 10 microseconds, but in the 1970s, we could only do as well as 1 millisecond, and so that annual cycle would essentially have been unobservable. So I'm going to close now by showing you a video of sea surface height variations that are determined from JSON-2 and other satellites, just to show you the power of satellite altimetry. So it's going to show you JSON-2 flying along the west coast of North and Central America. And you'll see it's simulating radar pulses, collecting radar altimeter data. There'll be green pulses going up to the satellite from the simulated SLR stations. This was a video produced by our team members at JPL. So I'm going to stop the video here just for a moment. So you see the crosshatch pattern, which is the ground track pattern of the JSON-2 satellite. And then you see the different colors represent the highs and the lows. And this particular pattern that you see here is representative of the El Nino signal. So when you have an El Nino that propagates into the eastern Pacific, you get a pool of warm water that propagates across the Pacific up to the coast of South America. And that's a signal that you can see in your altimeter data. And then if you can synoptically see as a function of time how you can map the changes in the ocean surface. Okay, so we can go back to the next slide. So in the introductory slide, I showed you regionally how we could compute mean sea level using satellite altimetry. We can also average the data over the entire globe. And so we can get a picture of how global mean sea level has changed as a function of time. And you see here represented the data from the different missions, TOPEX, JSON-1, and JSON-2. And so the current linear rate is on the order of 3.4 millimeters per year. So just to summarize, the Earth is a dynamic planet. In order to operate a system of altimeter satellites to monitor the variations in topography, we have to rely on precision tracking systems, satellite laser ranging, Dorris, GNSS. We have to very precisely describe the models that perturb that orbit, and we must model in detail the observations. So we need a very precise terrestrial reference frame, which is typically updated every 5 years. We need precision models of the Earth's gravity field, and that includes the time variations. We need to model the mass motions of the atmosphere. That's not something I've discussed, but for that we rely on atmosphere models like ECMWF and NCEP, and we need polar motion and Earth rotation information provided on a daily basis. And just one final point, if you're a user of altimeter data, you are reliant on radio telescopes measuring the orientation of the Earth from quasars. So something to think about. Thank you.
Okay, thank you, Frank. Thanks, everybody. What we'll do now is we'll move to a final set of polling questions. And I'd like to give these questions just a couple of minutes or so. We're running just a little bit over here. And from there, we'll move directly to the Q&A portion of this webinar. So be sure to stay in the room and or stay on the line to participate in the question and answer period. Right, thanks, everybody. We'll give these just a couple of minutes. Okay, everybody, at this point we're going to move to the Q&A period. And as I'm giving everyone an opportunity to type in some questions, I just wanted to make you all aware that in the lower right-hand corner of your screen, there is a file sharing pod. And what you'll find there is you've got both of the animations have been uploaded as well as the agenda, and the presentation today, both in PDF format as well as PowerPoint. So if you were to left-click on any of those files, you should be prompted to download the file. Okay, and then a listing of all of our upcoming webinars will be posted at the URL you find to the left. You can connect with us. We do have a Twitter, Facebook account. All of our webinars are posted to the YouTube channel within a couple of days of completion. All right, do we have any questions here? There's got to be a question. Okay, great. So, Frank, our first question is, could you please explain a bit about perturbation acceleration with relativity Schwarzschild? I may have not pronounced that properly at the end, but...
It's the it's a relativistic modification of the central body term. And so it's what gives you the advance in the perihelion of Mercury. You can think about it that way. And so it's an effect, as you saw, I don't have that slide in front of me, but it's something you have to account for. And if you don't, then you're going to introduce an error in your orbit propagation. Relativity doesn't just enter into the force model; it also enters into the modeling of your measurements as well, and into the computation of your time systems. It can get quite involved.
Okay, thank you, Frank. The next, she said, thank you, very great presentation. The next question is, how close to real time are the solutions? So
I'll speak for the JASON project just as an example, since that's the one I'm most familiar with. There are probably three categories of solutions that are produced. The first are the solutions that are produced in almost near real time. And there are two solutions that are produced in near real time. One comes from the GPS system, and that's merged with the altimeter data and disseminated. And the second, the Dorris system has a Kalman filter on board to actually do a solution in near real time, and that's merged with the altimetry and disseminated. And so there are papers which I can send to you if you email me that describe the accuracy of that near real-time ephemeris. It's typically radially on the order of a few centimeters. It's pretty good.
Okay, thank you, Frank. The next question is, if the GPS satellites are used for orbit determination, how are their orbits determined? And then further, to what level of accuracy?
The GPS satellites I sort of skipped that because I was running low on time, but it's also a complicated topic. So there's an international service called the International GNSS Service that sort of organizes and federates the different GNSS systems, sets quality standards for the stations, and analyzes the data. And so there are probably on the order of 8 to 10 international analysis centers that are signed up to analyze data from different GNSS stations, and they produce products on a regular basis. And those products are available at the IGS data centers. They're available at the CDDIS. And if you go to www.igs.org, you can get more information. So typically, what their precision that they have right now, it's on the order of a few centimeters. It's pretty good, and they get a really good estimate because they can intercompare all the orbit solutions from the different analysis centers. I hope this answers your question.
Okay, thank you, Frank. And I've just included the NASA Crustal Dynamics Data Information System URL for everybody here. Okay, so your next question is, you mentioned we need to know the position of the satellite relative to the center of the Earth. How do you define the center of the Earth? And then the second part is, are there any issues converting this geocentric position to geodetic latitude, longitude? And if you need me to repeat that, I can.
So you define the center of the Earth is defined to be the center of mass of the Earth system. That's what it is, because your satellite is orbiting around the center of mass, and it's presumed from your modeling and your equations of motion that you're orbiting around the center of mass. There is a small wrinkle to that, in that up until very recently, this is probably more detail than you wanted, but we didn't consider that the actual center about which the spacecraft is orbiting is not the same as what we assume in our reference system. And that deviation is caused by the motion of fluid on the surface of the Earth, so either the atmosphere or the oceans and so on. And so that geocenter motion is on the order of a couple millimeters in X and Y and up to 5 millimeters in Z. And it's one of the big signals that we want to measure in space geodesy, but we also have to model it in satellite altimetry. There is no issue about conversion between geocentric and geodetic. When we integrate the equations of motion, we're integrating everything in a Cartesian coordinate system.
Okay, thank you, Frank. I'm looking to see whether or not there are any additional questions. And in the meanwhile, just to let everybody know, when we're finished with the question and answer period, what will take place is that I will leave the virtual meeting space opened for an additional 10 minutes for those of you who may wish to download the presentation materials, but we will hang up from the telecon. We'll give it just another couple minutes or so to give people an opportunity if you have a question.
Don't be bashful.
And as a reminder, I may have mentioned this, I believe, at the beginning, but in order to download the presentation files after we are finished here today, the additional 10 minutes has passed. What you can do within the next couple of days, you'll be able to download those files by accessing this webinar at the tinyurl.com Earthdata webinar to the left. And basically, you would scroll to the end of the recording, and the file sharing capability is a persistent feature, so you would be able to download the files at that point. When you're listening to it by way of YouTube, you would not have that capability. And certainly feel free to email me with any questions. If you'd like to follow up with Frank offline, that's not a problem at all. Are there any further questions? Okay, great. We've got another question here. And the question is, do any of these measurements affect the very accurate location of aircraft?
Well, does satellite altimetry affect the location of aircraft? No, they're independent. But GNSS is used in all modern aircraft today. And so they rely on having knowing where the GNSS satellites are, but they're not relying on a precise orbit determination. They're using an ephemeris that essentially comes down with the GPS signal.
Okay, thank you, Frank. And the next question here is, you mentioned that GRACE data is not consistently available. Are there any plans for a follow-on mission to continue the sorts of measurements being made by GRACE?
Yes, there's a GRACE follow-on mission that's being developed. It's being developed by the U.S. And Germany, so the same partners. And so yes, the time series will continue, but one of the concerns is that the GRACE spacecraft itself is, getting old. It's been in orbit now for close to 13 years. And so they have to cycle the batteries essentially, I think it's every 170 days, and just turn off some of the instruments. And so there's a period of time where you don't get data, and because some of the systems now are single string, it could stop working at any time. So one of the big concerns is there could be a data gap between now, or between when the GRACE spacecraft might cease functioning and when GRACE follow-on is actually launched. That's just something that we'll have to deal with, and we'll have to use other satellite data, which is not quite as precise and not quite as detailed until the GRACE follow-on spacecraft is launched.
Okay, thank you, Frank. And the next is more of a comment, and it says, slide 35 is one of the nicest illustrations of continental drift I've ever seen.
I would urge you to go look at that website for ITRF 2014.
Okay. Are there any further questions? We are now in the extended Q&A period, which will end at 3:15 p.m. And again, I will leave the virtual meeting space open an additional 10 minutes. So certainly if you think of something, feel free to type that into the Q&A log. If there are no further questions at this point in time, I'd like to thank everybody for joining us this afternoon. I guess it could be morning or evening, depending upon where you are. And we hope to see you at a later point for an upcoming webinar. Any takers? Thank you. Thanks everybody for joining us. At this point, we will log off from the telecon. You're very welcome. All right, thanks everybody. Bye-bye now. Thank you, Frank.
Bye.
Bye-bye.